Hi, my name is Griff Malloy, and today I'll be talking about orbital debris removal using a traveling salesman method. What is orbital debris? Orbital debris is any sort of junk left over in space, ranging from paint chips to abandoned satellites. Around 13,000 pieces of debris are known, but it's estimated there's tens of millions of smaller pieces. The main problem is in low Earth orbit. This is because a vast majority of the satellites which we rely on daily operate in low Earth orbit. Harmful effects with human operations are caused with debris. Say an astronaut working on the ISS is struck by a piece of debris. They could either be harmed or killed. The worst effect is demonstrated in Figure 1, called the Kessler syndrome. It's when, say, two satellites crash into each other, creating a cloud of debris. That debris crashes into more satellites, creating more debris, and so on, causing a cascading event. But what is the traveling salesman problem? The traveling salesman problem was formulated in 1930 and is the benchmark for optimization. It has many applications today, involving logistics, wiring for microchips, and DNA sequencing, to name a few. The problem is defined as, given a list of cities and the distance between each pair of city, what is the shortest possible route that visits each city? Looking at Figure 2, the shortest possible route is 1, 2, 4, 3, 1, producing a route distance of 80. I'm going to talk about 3 different methods to solve the traveling salesman problem. Lexicographic ordering is a brute force method to solve every possible route. A 2-op swap, randomly changing 2 city locations on the route, and simulated annealing, using probability to find the global optimum for the given route. Lexicographic ordering. We have cities 1 through 5 in this example. What this method does is it tries orders 1, 2, 3, 4, 5, and then 1, 2, 3, 5, 4, 1, 2, 4, 3, 5, and so on, all the way to 5, 4, 3, 2, 1. This means it tries every possible solution and finds the best distance between them. The number of solutions is equal to the number of cities factorial, meaning in this case we have 120 solutions. With 6 cities we'd have 720, with 7 cities we'd have 5,040, and so on. Due to the nature of this, routes with more than 10 cities are not feasible, as a route with 11 cities would have over 39 million possible combinations. The 2-op swap. The 2-op swap is a random permutation of the current route order. In this example, we have 1, 3, 4, 5, 2, and we interchange the second, third indices to 1, 4, 3, 5, 2. We have it run for a set number of iterations because one of the major flaws is that the problem usually finds the local minima. This is demonstrated in Figure 4 and 5. None of the routes can be improved with 2-op swaps, however, Figure 5 has the more optimal route. So to negate this, we usually run the 2-op swap method a few times, we average the best route, and then we use that route as the starting route for the next iteration. In this example right here, I've limited both of the solutions to 300 iterations. Figure 7 has the more optimal route compared to Figure 6, as in the end it solves for a distance of 3, 1, 7, 5, 6. But looking at this, we know that we could easily improve it with a swap between cities 1, 7, and 8. Towards the end of the route, the path between city 1 and 8 crosses over the path between city 7 and 5. This isn't optimal. It can easily be fixed with a 2-op swap, hence why we average them and try it again. Simulated annealing. This is one of the more complicated algorithms, and it's inspired from metallurgy, where controlled cooling equals less defects. Just like the 2-op swap, this starts with a random initial guess, but this actually explores the nearby area. In exploring the nearby area, it picks less efficient routes early on in order to find the troughs of the world's minimas. After finding the troughs, the algorithm should be able to pinpoint the global minima. It has 3 constraints: the total number of iterations, the rate of cooling, and the total number of iterations at each temperature. Here's a quick rundown of the pseudocode for simulated annealing. We have the maximum number of iterations. Within that we have the maximum number of iterations at each temperature, the sub-iterations. What this does is it performs a 2-op swap of the old route compared to the new route, and then it calculates the distance, or the cost function, which in this case is the distance. So if the distance of the new route is less than the old route, then it sets the distance old equal to distance new, and it reruns for that iteration. But if the distance of new is greater than the distance of old, it calculates a probability function, doing the exponential of distance old minus distance new over temperature. And this produces a value between 0 and 1. That probability function is then compared to a random number between 0 to 1, and if it's greater than the number, you set the old equal to the new, and you end the loop. down in the temperature value where it says temp is equal to temp times alpha, you set the alpha as a number between 0.9 and 0.9999, so on. This causes the temperature to decrease at the end of each sub-iteration. So later on, the probability function will produce very, very small numbers, giving it a smaller chance of being greater than a random number, so it won't set the old equal to the new. This is demonstrated in these three figures right here. It's towards the end of the iteration, but the figures will loop over, so you'll be able to see what I'm talking about. Watch figure 8 in the upper right-hand corner. We have the temperature the temperature drops very fast because we have the alpha set to 0.95, which means at the end of each iteration, the temperature is multiplied by itself times the 0.95, causing it to drop very fast. What happens, and as you're seeing right now, is that it solves for a route, but it gets stuck in the route because it's not able to jump out of that cross. This is solved by changing the alpha to a higher number, demonstrated in figure 9. When this ends up solving for the solution, it takes a while, but it finds the most optimal path. Figure 10, on the other hand, has an alpha which is too high for the number of iterations. This isn't usually a problem because we could extend the number of total iterations, and eventually this would hone in on the global minima, but it's very time-consuming and very computationally expensive. Watching the paths now, in figure 10, it's still jumping around randomly because the system is like under-constrained in a sense. It won't hone in it on time. Figure 9 has almost found the optimal solution, but is still jumping around a bit comparing different values. And figure 8 is locked into the inoptimal solution that it has right now, and it won't be able to jump out of it. So, how does this method apply to orbital debris? Well, orbital debris such as iridium-33 or the Funging 1C orbits, it orbits the Earth in a shell. And the only difference between all the orbital parameters in the shell is the inclination and the right ascension of ascending node, because most orbits in low Earth orbit are circularized and they tend to stay relatively similar to each other. So, using the traveling salesman problem, the delta V can be calculated between each piece of debris, and that will be set as the cost function. We can use simulated annealing, shown in figures 11 and 12, to perform a RAN walk between all the debris. The pictures with the darker colored dots have a higher RAN, and the pictures with the dots with the lighter colors have a lower RAN. This means that we could eject a satellite into any position on the orbit with a RON, and we could start it off at any point and then continue around the RON walk. All of this is circular. In conclusion, orbital debris has become more of a problem recently. From a runaway Kessler syndrome, think about the movie Gravity, to dangerous working conditions for astronauts, debris must be taken care of soon. Using a traveling salesman problem algorithm is a good preliminary estimate of the delta V required to deorbit and contain these pieces of debris. Though the solution is far from optimized, it provides the close estimate. With current methods of propulsion and orbit transfer, a good upper estimate is 10 pieces of debris removal per year. The only problem with this is the debris is dynamic. It's not going to stay in those constrained orbits or anchor RAN slots as shown in the previous picture in the RAN walk. So to fix this, we need to come up with a dynamic solution to solve for moving cities. This requires a lot of computational power and a lot of optimization, such as what we're doing in class for homework right now. But in general, static traveling salesman problem gives a good overview, proving that removal is feasible in the near future. To end this, I'm going to demonstrate my MATLAB code real quickly, which I will paste in the text file later for you to run. You can run it. I'm going to pick 25 cities. I don't want them constrained. I don't want city numbers on the graph. I don't want to make a GIF. I'm not going to do lexicographic order. I'm not going to do up swap. And I'm just going to run through simulated annealing. It's going to pick some temperatures for you that I've hard-coded in, or you can pick your own. And you can watch it and play around with it and choose different numbers and different temperatures to see how the simulated annealing actually works and to solve for the most efficient path between all the cities. Thank you.